This is a meeting of engineers of the Flight Crew Support Division of the NASA Manned Spacecraft Center. The Flight Crew Support Division supervises the design, development, maintenance, and operation of all flight crew training equipment. The division directs flight planning and simulation activities for specific missions and for the support effort related to crew briefings and debriefings. They are responsible for the development of post-flight crew performance reports and support for checkout activities. They also furnish the coordination effort and analytical and consultation services in the areas of crew operational procedures, crew safety, technological and scientific flight crew instruction, crew station design, mission plans and systems operations, and flight crew-oriented scientific experiments. One of the Flight Crew Support Division's areas of charter is the procurement, management, and operation of trainers for the astronauts. Here an astronaut prepares to run a retrofire sequence in the Gemini Part Task Trainer. The procurement, design, and operation of systems trainers is another charter area. These trainers are breadboard mock-ups of the systems in the Gemini spacecraft. Light paths show the operation of the systems as related to the activation of the system's components. These trainers undergo constant modification with approximately 1 week configuration lag time between actual system and systems trainer. In conjunction with the systems trainers, the Flight Crew Support Division gives systems operation support to the flight crews. This consists of systems briefings, having up-to-date data available, and being able to answer systems questions posed by flight crews. This Saturn launch abort simulation is a part of the program of analyses, simulations, and operational tests of flight phases, including launch, powered maneuvers, and re-entry. The Crew Safety and Procedures Branch evaluates the flight crew's role as onboard controller and supports the astronauts in defining recommended backup control modes that will assure operational flexibility and safety. This effort recognizes mission operational constraints and emphasizes methods compatible with both automatic and manual functions in both the launch vehicle and the spacecraft. Liaison with program offices and operations divisions ensures adequate consideration of all operational requirements. This is a laboratory test for the Agena Flashing Rendezvous Light, a continuing project to evaluate various light sources and configurations. The Flight Experiments section evaluates experimental proposals for possible inclusion on Gemini or Apollo flights from the crew operational standpoint. When an experiment is approved, the experimental equipment to be used on the flight is designed, built, tested, and qualified. It is then positioned for storage in the spacecraft. The Crew Procedures Development Trainer is used for this purpose. This trainer is also used in the area of crew station requirements and evaluation. Contractor data are used to build a mock-up of the crew station. Flight Crew Support Division engineers, working with the astronauts, then evaluate the various aspects under consideration and point out problem areas to the contractors. The Flight Crew Support Division is responsible for the pre-flight and mission training of the astronauts. This includes the area of academics, such as this geology class, as well as contingency training, environmental familiarization, flight simulation, and the Space Readiness Program. Support is given to the Flight Acceleration Program now being conducted by the Manned Spacecraft Center in the centrifuge at the Naval Air Development Center at Johnsville, Pennsylvania. The centrifuge is used for mission training and engineering programs. Another flight acceleration facility is being built at the Manned Spacecraft Center in Houston. The Flight Crew Support Division conducts pre-flight technical briefings for astronauts and technical personnel, such as this one on the Apollo spacecraft. Support to post-flight technical debriefing was provided during the Mercury program and is to be continued throughout the Gemini and Apollo flights. In October and November of 1963, the Crew Station branch of FCSD conducted a study to investigate LEM lunar landing requirements as a function of brightness levels. A helicopter with a modified LEM window installed was used on LEM trajectories from 1,000 feet altitude to the surface. Observers wore neutral density filters to simulate brightness levels from 1/4 Earth shine with lowest lunar albedo to full Earth shine and maximum albedo. Engineers and astronauts from the Manned Spacecraft Center and engineers from Grumman Aircraft participated. The ability to select a landing site, the trajectory utilized, and window visibility requirements were evaluated in various lunar brightness levels.
Run number 58, trying 1635, good leopard simulated, .001. 1. I see a pretty good spot dead ahead. We should get down a little bit faster. I'd increase my translation downrange a little bit. I see a light area dead ahead. It looks plenty big enough. It's slightly right now. Plenty big enough if it is smooth enough, and I can't tell yet. To have the right spot in mind, just to the left of all of those white dots. Contrast is not good, but I would commit to a landing here now.
The site selected was the Pisgah Crater lava flow in California, which closely resembles known lunar surface characteristics: homogeneity, monochromatic qualities, low albedo, no vegetation, and little or no man-made construction. This is how the same landing area appears through the neutral density filters. The participating observers directed the pilot through the trajectory to the landing site they selected. Comparative landing times were studied as a function of fuel used under various brightness levels. Although an actual landing was not made, commitment to the site was achieved. The window configuration, minimum brightness levels to detect, select, and land at a satisfactory lunar site, and trajectory shape as a function of brightness level are now undergoing final evaluation. Another project of the Flight Crew Support Division is the investigation of a window located overhead of the Command Astronauts Control Station in the Lunar Excursion Module. The hardware consists of a mock-up of the LEM crew station constructed of wood and cardboard for quick and easy modification. The window is made of 2 sheets of plexiglass with crosshairs etched on each sheet. The window is mounted on a sliding track. This facilitates the portion of the project concerned with finding the optimum location for this window. A sidearm controller representing the LEM attitude controller is operated by the pilot. This is connected by means of 2 aluminum rods to a collimated light source. When the control handle is operated, the light source operates in the pitch and yaw axes corresponding to the controller movement. A spot of light is projected on the ceiling and represents the horizon with reference to the alignment of the LEM. This will later be replaced by a horizon line and star background reticle. Pilots wear a pressure suit in both a pressurized and non-pressurized state. The pilot is restrained by harnesses. A simulated launch is flown by the subject from the lunar surface to orbital insertion. After the start of the run, the pilot aligns the spacecraft by means of the projected light beam horizon and the markings on the window. The accuracy of the alignment is checked by means of protractors and pointers attached to the light source. The actual use of the overhead window for docking was not investigated in the initial phase. However, the area of the command module visible from the LEM through the overhead window configuration was determined. Studies of the overhead window configuration have already resulted in the elimination of the front docking ring. This results in a weight saving and simplicity of operation on the lunar surface and during injection into orbit from the lunar surface. The docking mechanism, located in the upper ring, need not be transferred during the ascent phase. The front hatch will be retained, however, for access on the launch pad and for lunar ingress and egress. Traversing the hatch is simplified as the astronaut will not have to crawl through a tunnel in a pressurized suit. Should an abort situation occur, the window could be used to control the LEM's attitude. Tests of other aspects of the overhead window usage are now underway. In May 1964, the Flight Crew Support Division put into operation its Gemini Crew Procedures Development Trainer. This is a full-scale Gemini Crew Station mock-up built by the Manned Spacecraft Center Technical Services Division under the supervision of the Crew Station Arrangement Section and Spacecraft Operations Branch of FCSD. This provides a test bed for development and evaluation of experimental equipment and inside-out evaluation of optical and photographic equipment. The interior is identical to that of the Gemini spacecraft. Hardware items such as switches, warning lights, meter readouts, and ejection seats have been used where possible to ensure authentic interior configuration. The Crew Procedures Development Trainer also provides a current crew station for conducting crew task evaluations, to familiarize flight crews with manipulation, operation, and storage of operational and experimental equipment, to provide an environment for the integration of crew and equipment, and to develop flight procedures in the use of crew-oriented equipment. Regular modification of the Crew Procedures Development Trainer will keep its configuration concurrent with that of spacecraft to be used in coming missions. On the fixed base docking simulator at NASA's Langley Research Center, studies were conducted to determine the adequacy of Gemini hand controllers, displays, and attitude modes during the docking phase of Gemini missions. Visual cues are provided by closed-circuit television and a model of the Agena target vehicle. The Agena model can move through 3 translational degrees of freedom. The television image is reflected from a gimbaled mirror onto a spherical screen. The movement of the mirror provides azimuth and elevation motions. Astronauts participated in the studies by flying the simulations, then commenting on various aspects of the docking procedure. Parallel studies were run in the moving base docking simulator, also located at NASA's Langley Research Center. The same pilots participated in this phase. Debriefings were conducted along similar lines to the television simulation debriefings, and pilot reactions compared. Data for the simulations are fed into the system by analog computers. The crew station is suspended from a moving framework and is hydraulically driven. Black curtains around the Agena target vehicle hide visual cues which the pilot would not have during an actual mission. Also studied at this time were the Agena paint scheme, docking aids, lighting systems, and control system deadband. The Gemini Part Task Trainer is a former Mercury simulator modified to the Gemini configuration. In the Part Task Trainer, the astronauts can align the Gemini spacecraft during a simulated orbit and practice retrofires. Analog computers interpret control actions and supply data to the displays and instruments which simulate the motions of the spacecraft. A star background is projected in the crew station window to give the astronaut visual cues for spacecraft alignment and to add realism to the simulation. This star background is created by an infinity optics unit through the spacecraft window. A black sphere with highly reflective ball bearings in its surface provides the basic celestial field. The ball is gimbaled and responds to computer commands. A gimbaled unit contains the light source for illuminating the sphere. The masking arrangement occludes the light when the spacecraft is in an attitude pointing at Earth and provides a visual Earth horizon. A closed-circuit television system is now being studied to be used in conjunction with the celestial display and will eventually be incorporated on the Gemini mission simulator. This will give a rendezvous and docking display capability with a target vehicle. The rays from the gimbaled light source are focused by a series of lenses to a point at beam splitter number 1. The light then shines on the surface of the sphere, is reflected by the ball bearings, back to beam splitter number 1. It is then reflected to a spherical mirror, and from there back through beam splitter number 1, through a corrective lens, through beam splitter number 2, and onto the surface of beam splitter number 3. Light from the television monitor reflects from the surface of beam splitter number 2 and mixes with the light from the celestial sphere. The combined image is then reflected from beam splitter number 3 to the surface of a second spherical mirror. The light is reflected by the mirror in collimated rays through beam splitter number 3 and is seen by the observer. The star background is seen as if at an infinite distance, while the television image is capable of appearing at finite distances. While the astronaut flies the simulations, instruments monitor and record his performance. The instructor in charge of the simulation and the astronaut can evaluate the performance and increase flight proficiency. The Gemini Mission Simulator is a major piece of hardware now being used by the Flight Crew Support Division in the astronaut training program. There are two such simulators. One located at Cape Kennedy will be used for specific mission training. The other is being installed at the Manned Spacecraft Center in Houston to be used for general training. In these simulators, entire Gemini missions can be flown. The crew station is a replica of the Gemini spacecraft. The Cape Kennedy configuration will be that of the spacecraft for the upcoming mission, while the Houston configuration will be that of the following mission. Visual displays will be provided by an infinity optics window and give the simulator rendezvous capabilities. At the Environmental Control Station, crew station temperature can be controlled from approximately 60 to 90 degrees Fahrenheit. Suits can be pressurized to a 3.5-pound differential. Two digital computers supply data for the simulations. The DDP-24 computer supplies data for guidance and other aspects. The Mark I computer provides environmental control and other facets. The simulation is controlled at the instructor station. Controls and readouts on the display panel duplicate those in the crew station. Although systems failures are programmed into the computers for a specific simulation, failure buttons on the instructor's console can override the computers or introduce other failures either gradually or abruptly. Television cameras in the crew station transmit pictures of the pilot's performance to monitors at the instructor's station. Digital clocks show elapsed time, and a moving map gives the theoretical location of the spacecraft during the simulation. The instructor can store any portion of the simulation in the computer and rerun it. Telemetry failures can be introduced at the telemetry monitor console. This exercises flight control personnel who are also training during the simulation. Magnetic tape and flight recorders provide a permanent record of the simulation. At present time, the GT-3 primary and backup crews are undergoing training. The astronauts will spend many hours in these simulators before flying actual missions in space.